Right triangle trigonometry is the classic development of trigonometry. And it's based on this idea. If we take a right triangle, then from the perspective of a particular angle, like this angle I've labeled theta, there is a side which is opposite this angle, there's a side which is adjacent to this angle, and the side opposite the right angle in the right triangle is called the hypotenuse. So there's an opposite side, an adjacent side, and a hypotenuse. And with those sides labeled that way, we can create ratios among the sides. And we'll talk about those ratios in a moment, but they have particular names. And there are 6 ratios, 6 names, and those names are sine, cosine, tangent, cotangent, secant, cosecant. And each one of them has a different ratio involving the side. So from the perspective of this angle theta, the sine of theta is the opposite side over the hypotenuse. So it's this side over that side. And it's just a fraction or a ratio, and we'll see how useful it becomes in just a little bit. But now, so sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, so it would be this side over the hypotenuse. Tangent, the tangent of theta, is the opposite side over the adjacent side, opposite over adjacent. And then for the others, cotangent of theta is adjacent over opposite. Now, here's what I want you to notice just right here at the beginning, that tangent was opposite over adjacent, cotangent is adjacent over opposite. You see, these happen to be reciprocals of one another. And then when we get to secant, secant is hypotenuse over adjacent. Now that's hypotenuse over adjacent. And that then is the reciprocal of cosine. You see, cosine and secant are reciprocals of one another. And then maybe it's no surprise that cosecant and sine are going to be reciprocals. Cosecant is hypotenuse over opposite, and this is opposite over hypotenuse. Now the reciprocal ideas are not as easy to see when listing the trig ratios like this. They're a little easier to see like this. Let me show you up here. Sine and cosecant are reciprocals. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals. Now, that kind of makes the whole situation a little bit easier, because if we know about these reciprocals, then all we need to do, if we're going to generate all of the trig functions, and these are either, we can think of these as trig functions or trig ratios. I think the ratio idea is a little easier when we're talking about right triangle trigonometry. But we can generate all of these ratios pretty easily just by generating the first 3, that is sine, cosine, and tangent, and then use the reciprocals for the other 3. Let's go through a problem or two. Here we have an angle theta and a triangle that is labeled with this side of length 3 and that side of length 4. Now, in order for us to write the various ratios involved, we need the lengths of all 3 sides. Now, if we're only given 2 of the sides, as is the case here, we figure the length of the third side by using the Pythagorean theorem. So we know that c squared is equal to a squared plus b squared. And these are the legs of the right triangle, you see, and there's the hypotenuse. And that's the side c in this relationship. So c squared then is, well, let's see, one of these is 3, the other is 4. So c squared then is 9 plus 16, or 25. If c squared is 25, then c is plus or minus the square root of 25. And we want the positive square root of 25, or 5. So the length of this side is 5. Now with that information, we can generate our various trig ratios. Let's see, from the perspective of this angle, and the perspective is very important, because if we're talking about the sine of this angle, it's 4 over 5. It's opposite over hypotenuse. But if we're talking about the perspective of that angle, then the opposite side would be 3 and the hypotenuse 5. So it changes things a little bit when we shift to the other angle. So we have to talk about a proper perspective here. So from the perspective of this angle theta, the sine of this angle is opposite over hypotenuse, or 4/5. The cosine of this angle is the adjacent side over the hypotenuse, or 3/5. The tangent of this angle is the opposite side over adjacent, so it's 4/3. The cotangent is, well, let's see, it would be adjacent over hypotenuse. But you know, we realize that these are reciprocals of one another. So the cotangent of theta will just be the reciprocal of 4/3, 3/4. And in a similar way, secant and cosine are reciprocals. So the secant of theta is going to be the reciprocal of 3/5 or 5/3. Cosecant and sine are reciprocals, so the reciprocal of 4/5, 5/4 for the cosecant of theta. So to complete the little diagram here, it's kind of like this. Now let's talk about the various trig ratios on particular angles. And the particular angles that we're going to start off with are angles that are going to be important to us as we go along. It turns out that we're going to use the sine, cosine, tangent mainly of angles of 30 degrees, 45 degrees, and 60 degrees so often that you're going to end up committing these to memory. And you're going to be able to remember them, not from memorization, but from use, and also from a little diagram, a little associated right triangle that we're going to talk about here. So here's the development of the idea. We're going to talk about the various trig ratios on a 45-degree angle to begin with. Now, I have the lengths of sides unlabeled, but here's what we understand about this triangle. Just knowing that this is an angle of 45 degrees, and knowing that the sum of the angles in the triangle is 180 degrees, and that's 90 degrees, then these two total 90, and therefore that rascal has to be 45. Okay. Now, I'm emphasizing that idea because it gives us a special kind of right triangle. And that special kind of right triangle is isosceles. This is an isosceles triangle because two of the angles are of the same measure. Now, if the two angles are of the same measure, then the sides opposite those angles are of the same length. So these two sides have the same length. Okay, now, we want to do some labeling here. We want to put a label on those sides. All we know right now is that these are the same length. It could be 2, 2, 5, 5, 15, 15, doesn't make any difference. Then we could find this one. And it turns out that it really doesn't make any difference what value we put on these two sides and then subsequently have the value of the hypotenuse, because the ratios are going to be identical in all of those cases. And it goes back to this idea that, and you may have studied problems like this in the past where you might be trying to find the height of a tree or the height of a flagpole, and you need to do it indirectly. You can't measure it directly, and so you set up a situation involving the length of the shadow of the tree or the flagpole and something like that. And you make similar triangles, and it's the similar triangle idea that's so important here. That similar triangles have the characteristic that corresponding sides are proportional. Proportional. Now, what that means is this, that if I have an angle, let's say here's my theta. All right, now, is it easy to see that if I extend this side and this side, I'll have a new right triangle, but because this angle theta is the same as the angle theta in this smaller right triangle, you see, for the larger right triangle, the triangles are similar. Now, similar triangles have the characteristic that they're the same shape but a different size. So these two triangles, the big one right here and the little one right here, are similar triangles. So corresponding sides are proportional, and that just means that the ratio of, from this perspective, the ratio of this side over that side for the small triangle is equal to the ratio of this side over that side for the larger triangle. And we can generate larger and larger triangles all day long like this, you see. For whatever triangle we choose, the ratio of two sides is going to be the same as the ratio of two sides in any other triangle in this group. Okay, now if we change the angle, everything, all bets are off here. But as long as this angle stays the same, then this situation is true. Now that's important here because of the way that we are going to determine the sides of our right triangle. Now, If it doesn't make any difference about how long these sides are, you see, then I want to make this as simple as I possibly can. So I'm just going to make this side length 1, and this side is therefore length 1. And then I can find the length of the hypotenuse by using the Pythagorean theorem. C squared is A squared plus B squared. A and B are both 1, so C squared is 1 squared plus 1 squared. C squared then is 2. And if C squared is 2, C is plus or minus the square root of 2, and we want the positive square root, so C is the square root of 2. Okay. Now, we can generate our trig ratios. We have, let's see, from the perspective of this angle, and actually from the perspective of both of them because they're equal to one another, but at any rate, we're kind of used to dealing with an angle in this position. The sine of 45 degrees is 1 over the square root of 2. So we slide over here. This is 1 over the square root of 2. Now we may use it like this, or we may end up rationalizing. And if we rationalize, that's okay. It would be the square root of 2 over 2. So we could write it like that. It really depends on your teacher. Let me do this a little better. It really depends on the preference of your teacher. This is technically more correct to write it in rationalized form. All right, the cosine of 45 degrees, well, let's see, it's adjacent over hypotenuse, so it would be 1 over the square root of 2 as well. So 1 over the square root of 2. And it too rationalizes to the square root of 2 over 2. And then tangent 45 degrees is 1 over 1, which is simply 1. Now, for the cotangent, secant, cosecant, we just look at reciprocals. So we have, let's see, the cotangent is the reciprocal of tangent, so that would be 1 over 1 as well, or simply 1. Secant 45 degrees is the reciprocal of cosine, so it would be, flip this over, and it would be simply the square root of 2 over 1, the square root of 2. And then cosecant and sine are reciprocals, so let's see, the reciprocal of 1 over square root of 2 is the square root of 2. Now, I think at this point it's important to realize that we are talking about the trig ratios for some angles that are going to occur very often in our study of trigonometry. And so we're going to remember these values, and we're going to remember them from great use and not from memorization. I don't suggest that we go try to memorize these right away. We can always drop back. If we forget these, we can always write this little reference triangle, you see, and help us with the ratios, to help us with generating those ratios. So this is our basis for the study of those trig ratios, and not the memorization of those fractions. Okay. Now, also realize that we have a relationship between angles measured in degrees and angles measured in radians. So we might think about the radian counterpart here for 45 degrees, and it's pi over 4, you know, and so we could think that, gee, the sine of pi over 4 is also the square root of 2 over 2. And the cosine of pi over 4, you see, I could just replace all of these with pi over 4, and I would get the same result, as expected. All right, let's talk about the other angles, the other important little angles that I was mentioning, the 30 degrees and 60 degrees. Now, here's how that situation is generated. Here's how we want to think about it. We start with an equilateral triangle. That's an angle, excuse me, that's a triangle with all angles the same measure, the same opening, and every one of them is 60 degrees. So it's 60 degrees here, 60 here, and 60 there. Now, in order to create a right triangle situation so that we can study our ratios, we do this. We construct a perpendicular bisector from this angle down to this side. So we do this. Now, if it's perpendicular, then we have a right angle here. And if it's a bisector up here, then this is a 30-degree angle. All right. Now we have a kind of a neat situation here. Now notice that because this is a bisector, that whatever length side this is, that this distance is just half of that. You see, this is the same as that, and we're taking half of it. All right, now that's really important when we go through the business of just choosing values for the lengths of sides. All right, and we're going to do that right away here. That if I want to make the short side as convenient as I possibly can, then I would make it of length 1. And if this is 1, then that's also 1, and the whole length here is 2, and therefore that's 2. So this length is 2. Okay, so now we have a couple of sides labeled, and we can generate the third one by using the Pythagorean relationship. I'll just take off this part of the figure, and away we go. Now this one is one where we're finding the length of one of the legs. We know the hypotenuse is 2, but one of the legs is unknown to us. So let's see, we have c squared is 2 squared is equal to, now I'll let a be the 1 here, and we're finding b. So we have 4 minus 1, this becomes 1, subtracted on both sides, we have this. B squared is 4 minus 1, or 3. So b then is the square root of 3. Okay, so this side is the square root of 3, and away we go with our trig ratios. Now again, though, before we even get to the ratios, this is your basis for remembering the trig ratios. All right, this is our reference for those ratios. And this is often called a reference triangle for that reason. And now just notice that it is 1 to the square root of 3. 1 to the square root of 3. And the one side is opposite the 30-degree angle. All right, it's the short side. The short side of a triangle is opposite the smallest angle, always. And so no wonder this is the case here for this particular triangle. All right, now let's generate our ratios. We have, let's see, from the perspective of the 60-degree angle, and we're going to do both of them here for this little reference triangle, but for the 60-degree angle, the sine is the square root of 3 over 2, opposite over hypotenuse. So sine of 60 degrees, square root of 3 over 2. Cosine of 60 degrees, that's 1 over 2. 1 over 2, 1/2. The tangent of 60 degrees, square root of 3 over 1, square root of 3. The others are reciprocals of the ones above. Now we can emphasize the idea of rationalizing, but I'm not going to mess with it too much right now. I just want to emphasize, though, that these are reciprocals, and therefore the cotangent of 60 degrees is 1 over the square root of 3, which can be rationalized. And then secant 60 degrees is the reciprocal of cosine 60 degrees, and the reciprocal of 1/2 is 2 over 1, or simply 2. The cosecant of 60 degrees, let's see, the reciprocal of sine would be, flip this over, and we have 2 over the square root of 3. Okay. Now let's look at the perspective of the 30-degree angle. We want our trig ratios involving this 30-degree angle. And let's see, for sine, it's opposite over hypotenuse. Well, that's 1 over 2. So let's put that in up here. The sine of 30 degrees then is 1 over 2, 1/2. Cosine 30 degrees, from our reference triangle now, from the perspective of this angle, this is the hypotenuse, the adjacent side is this side, so it's adjacent over hypotenuse, so it's the square root of 3 over 2. All right, and over here, square root of 3 over 2. Tangent 30 degrees. From the perspective of this angle, the tangent is opposite over adjacent, so it's 1 over the square root of 3. Over here, 1 over the square root of 3. Now, for the other ratios, reciprocal of these two would be the square root of 3 over 1, or simply the square root of 3. For secant, it's the reciprocal of cosine, so it's, flip that over, 2 over the square root of 3. For cosecant, it's the reciprocal of sine, so it's the reciprocal of 1/2, which is 2. Now, all of these ratios that we're talking about for 60-degree angles and 30-degree angles are also true in radian measure. So we could replace the 60 degrees here with pi over 3 and have these same ratios hold true. And over here, for 30 degrees corresponds to pi over 6 in radians, so all of these could be replaced with pi over 6. Now notice another rather remarkable relationship. You may have noticed already that because we're dealing with the same lengths of sides here, and all we're talking about is a bunch of fractions involving the lengths of those sides, it's no wonder that we have some of the same fractions over here that we have over here. But there's a pattern to it. That the sine of 60 degrees is the square root of 3 over 2. The cosine of 30 degrees is also the square root of 3 over 2. Those two are the same. And the cosine of 60 is the same as the sine of 30. Those two are the same. Wow, and then look at this level. The square root of 3, the square root of 3, same. Tangent 30, cotangent 60, same. Secant 60, cosecant 30, same. Secant 30, cosecant 60, same. It seems to be the case that because we have a situation where 60-degree angles and 30-degree angles are complements of one another, it seems to be the case that a trig ratio applied to a certain angle is equal to the cofunction of its complement. Now that's a mouthful of math, isn't it? The cofunction of its complement. The cofunction of tangent is cotangent, and the complement of 60 degrees is 30 degrees, and these are equal to one another. Now the way you just realize it, and you don't have to say all of that every time you use this notion, but it's the idea that if we know, for example, the sine of 10 degrees has a certain value, then we know that value is equal to the cosine of its complement, which is 80 degrees. You see, we know that the sine of 10 degrees is equal to the cosine of 80 degrees. If we know one of these, then we automatically know the other.
An examination of the trig ratios allows us to identify certain relationships called identities. For example, now we know these are the names of the trig ratios, and they are abbreviated this way and they apply to angles. Now normally they are listed in the fashion listed here, but suppose we rewrite them like this. And we know that these all apply to some ratio or refer to some ratio, and here are the various trig ratios. Now consider changing these around like this, and consider flipping them over. Now before we do, we'll take the items on the right and write them over one. But writing the reciprocals of each of these allows us to see a relationship left and right. Notice that sine theta is opposite over hypotenuse, and opposite over hypotenuse is also 1 over cosecant theta. In a similar way, cosine theta is equal to 1 over secant theta, and tangent theta is equal to 1 over cotangent theta. In a similar way, cosecant theta is 1 over sine theta, secant theta 1 over cosine theta, and cotangent theta 1 over tangent theta. These are called the reciprocal identities. Another set of identities is called the quotient identities. These are the quotient identities. Let's take the top one here and simply verify it using trig ratios. Now, tangent theta is sine theta over cosine theta. Let's rewrite sine and cosine in terms of ratios. Sine theta, of course, is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. Now we have a complex fraction. We can consider this to be the top fraction divided by the bottom fraction, or simply rewrite it like this. Of course, when we're dividing fractions, we multiply by a reciprocal, and here we notice a nice cancellation. So tangent theta becomes opposite over adjacent. And that's the way we understand tangent theta. It is opposite over adjacent, and the identity is verified. In a similar way, of course, we could verify cotangent theta, or just understand that the cotangent is the reciprocal of tangent, and understand, therefore, that it is cosine over sine. Here's another group of identities, the Pythagorean identities. Now, let's take the top one here and consider where it might have emerged from. They're called Pythagorean identities for this reason. Consider a right triangle, and from the perspective of this angle, which we'll call theta, Here's the opposite side, the adjacent side, and the hypotenuse. Now, by the Pythagorean relationship, we know that the opposite side squared plus the adjacent side squared is equal to the hypotenuse squared. If we run through this relationship and divide through by hypotenuse squared, look at what happens. We have opposite over hypotenuse squared here, adjacent over hypotenuse squared here, and 1 on the right side. Of course, opposite over hypotenuse is the idea of sine, adjacent over hypotenuse is cosine, and we bring down the 1. Now, we usually rewrite this as simply sine squared theta plus cosine squared theta rather than putting the squared symbol outside of the parenthesis. Now, all of this, this verification was brought on by dividing through the top relationship by hypotenuse squared. If we had divided through by adjacent squared or opposite squared, we would have verified one of the other Pythagorean identities.
Let's use identities to solve this problem. It says, if sine theta is equal to 6/10, find cosine theta and tangent theta. Now, let's understand that we don't have to use identities to solve this problem. We could just take the tactic, well, if sine theta is 6/10, then I can make a little triangle here, a little right triangle, and if this is theta, then the sine of theta is opposite over hypotenuse, and I just need to make a fraction that's equal to 6/10. It could be 6/10 over 1, and I could make this 6/10 and this 1. Or I could say, well, 6/10 is 6 over 10, so I could make this side 6 and this side 10. Or I could say, well, 6 over 10 is the same as 3/5, so I could make this side 3 and this side 5. So there are a lot of ways to set up the situation using a triangle in order to go through and find the third side, you see, and then find cosine theta and tangent theta. All right, all of that's fine, but let's use identities here to solve the problem. Now, to use identities, here's what we do. We think, well, we have information about the sine, and we want to find the cosine of theta. Now, we need an identity, therefore, that involves sine and cosine. And the convenient identity I'm thinking about is the first Pythagorean identity that we looked at, and it was that sine squared theta plus cosine squared theta is equal to 1. And then we just plug in the information we know. We know that sine theta is 6/10. And we know that sine squared theta means sine theta all squared. So this becomes 6/10 squared plus cosine squared theta equals 1. This becomes 36/100. Then we subtract 36/100 on both sides. And on the left, we'll be left with cosine squared theta. On the right, we have 1 minus 36/100 turns out to be 64/100. And now if cosine squared theta is equal to this value, cosine theta is equal to plus or minus the square root of that value. We want the positive one of those two. So it's the square root of 64/100 or 0.8. Now let's find tangent theta. Well, one way to find tangent theta might be to look for an identity involving tangent and sine, but we've already calculated cosine theta, so we can involve an identity that has sine theta, cosine theta, and tangent theta in it. And that's pretty easy. That's the one that is tangent theta equals sine theta over cosine theta. Now, when you use identities like this, I suggest that you write the identity down as I have here and not try to plug into the identity as you go along. So I would write the identity and then kind of plug into it as though it were a formula from the past. So tangent theta then is, sine theta we know is 0.6, and cosine theta we calculated to be 8/10. So tangent theta then is 6/10 over 8/10, 6 over 8, or reducing 3/4. Here's a situation in which we'd like to solve for the length of a side and the size of the angle. Now here we weren't solving, in this previous problem, we weren't solving for the angle size, but we can solve for the angle size. Now consider that we want to solve for this angle, we want to solve for that side. Now certainly one way to solve for the side is to use the Pythagorean theorem, but let's use our trigonometry here to solve for that side and also for this angle. Let's go for the angle first. Now I have information about the side opposite that angle and the side adjacent to that angle. And so I want a ratio that involves the opposite side and the adjacent side. That would be tangent. So the tangent then of theta is equal to the opposite side over the adjacent side, 15/8. Now, think about tangent as though it's just an operation, just another operation, kind of like squaring or absolute value or something like that. Now, if it is an operation, and if we think about it like that, then suppose we think about, I wonder if there's an opposite operation to tangent, like undo tangent, you see. Now, if we can do that, if we can do this opposite operation over here, we have an operation on the angle. If we can undo the operation of tangent, then we'll have simply the angle here. And then we'll have to apply that undo tangent operation on the right side as well. Well, there is an undo tangent operation, and it's called the inverse tangent, or it's called arctangent. Now, so undo tangent over here, and we're left with theta. Undo tangent over here means arctangent of 15/8. Now there's another designation to this, and it is, in fact on the calculator, we're going to look for it on the calculator, and it's the second function on tangent, and you'll see the marking on it. It has TAN and then a little exponent of -1. So the inverse tangent operation is what that's all about. So we would use the calculator then to make this calculation. So we would find it to be, now let me write the steps in doing that. Here's what you do. You press second and then the tangent button. Now these two together, the second function on tangent is arctangent. Okay, a parenthesis will automatically open, and then you enter 15 divided by 8, close the parenthesis. Now the parenthesis is automatically opened on many calculators now, so I'm not opening a separate parenthesis here. It's already opened when I do this. All right, but you close it over here, and actually you don't have to close it in this particular circumstance, but it's wise to close parentheses that have been opened for you because of future kinds of more complicated problems that we'll run into. At any rate, we'll have 15 divided by 8, close parenthesis, and press enter, and we find the value here for the inverse tangent of 15/8, and it turns out to be approximately 62 degrees. So we have theta then is approximately 62 degrees. All right, now let's find x. And let's find x by using a trig ratio. Now, we have the value of theta. We know theta to be approximately 62 degrees. And I'll put that in here like this. Okay, so theta is 62 degrees. So we have the value of the angle, and now we just need to involve a trig ratio that has x in it, you see, with one of these two sides. Either one of them will work. How about the sine ratio? We have the opposite over hypotenuse. So the sine then of 62 degrees is equal to 15/x. And now we'd go through the algebra of solving this for x and then use the calculator to finish off the calculation. Well, multiplying on both sides by x. On the left I would have x sine 62 degrees equals 15. Now I'm writing the left side factors as x sine 62 degrees, and I caution you about that. There's a tendency sometimes to write the x factor on the other side, and if you do, you pretty much have to introduce a parenthesis. For this reason, if you're writing this as sine 62 degrees x, you see then just writing it like this, it looks like you're taking the sine of 62 times x. you see? And so if you're writing it like this, you have to have a parenthesis in here separating the two factors. But writing it this way, you don't need that parenthesis. Anyway, this is kind of a preferred way to do it. All right, now let's realize that sine 62 degrees is just a number in the calculator. So we have a coefficient of x here on the left side. And what do we do with coefficients? We divide on both sides by them. So what we're really doing here is this. We're going to take that coefficient and divide it on both sides. So we have this. These go out, and so x then is this fraction. And now it's just a matter of punching the calculator. Now, I do want to mention in this problem that I have created a situation where the value of x is not going to be exact here. And the reason it's not is because I estimated the size of the angle. The angle, remember, of 62 degrees was an approximation. And it was exactly arctangent of 15/8. You see, that's the exact value, but we approximated it, that angle, to be 62 degrees. So we're using an approximation here, not an exact value. If you put into this 62 degrees arctangent 15/8, then you would get an exact value for this fraction. But I just want to, it's close enough here for our study, but I just want to point that out, that whenever you use an approximation to calculate something else, then that something else that you're calculating is not going to be exact. Okay, anyway, this turns out to be approximately 17, and the exact value of x turns out to be precisely 17 feet. And I know that it's exactly 17 feet because I used the Pythagorean relationship on the original triangle to find it to be 17. But using this technique, it's approximately 17. It rounds to 17 very quickly. Here's a problem that it has a little more real-life flavor to it. Suppose we have a river, and it's a small river, stream. And we can identify a tree on the other side of the stream, or any object would work here for what I'm talking about. We want to find the distance across the stream. Now, and we can do that without actually crossing the stream and putting a tape measure across it and that kind of thing. We do it like this. Suppose we identify an object on the other side, like a tree, and suppose we identify a point on this side of the stream that's directly across the stream. Now, from this point, we walk downstream, let's say a distance of 100 feet. And then we measure the angle. Now this is straight across the stream, but from here we measure the angle across the stream to be, let's say, 50 degrees. Now, we're taking a few leaps here in terms of calculation and precision here. If we have some accurate surveying tools, then we could very accurately turn this angle and measure it to be 50 degrees. And there are little household sort of techniques for turning angles like this and measuring them. We're not going to talk about them right here, but there are techniques for doing that. But we have a right triangle situation formed here, and we're looking for the distance across the stream. So from the perspective of this angle, we have information about the adjacent side, and we want information about the opposite side. So when opposite side and adjacent side are involved in a ratio, it's either tangent or cotangent. Now, the tangent idea is in the calculator, so let's use tangent. So we make the calculation like this. We just say tangent of 50 degrees is equal to, from the perspective of this angle, opposite is x, adjacent side is 100. So the tangent of 50 degrees is x over 100. Multiplying by 100 on both sides, we have 100 tangent 50 degrees is equal to x. And now it's a calculator push. It's 100 times tangent on the calculator is just a button. And then enter 50 degrees, or just 50, and Press enter and we find the value of x. Now make sure the calculator though is on the degree mode and not radian mode for all of these calculations. I should have mentioned that earlier because it's a very important matter to get the right answer. At any rate, 100 times tangent 50 degrees turns out to be approximately 119 feet for the distance across this stream. Here's a problem that involves a space shuttle launch. Distances can be extremely deceiving when you're watching an unfamiliar event like a shuttle launch. And one of the reasons for that deception is the fact that the launch pad and the vehicle itself are so incredibly large compared to anything that we are familiar with. Now, suppose that we back away from the launch pad. Suppose an observer uses a map to determine the distance from a space shuttle launch pad to be 2.5 miles. Now let us suppose that a few seconds after liftoff, at one particular moment in time, the observer uses some sighting instrument to measure the angle of elevation to the base of the shuttle to be 25 degrees. So at this moment in time, we measure that angle to be 25 degrees. Now, how high is the shuttle at that particular instant? Well, let's assume that the shuttle is still moving vertically and we can make our calculation. Now, we're looking for the height of the shuttle, and a right triangle is formed, so we can use the tangent relationship or the tangent ratio. From the perspective of the 25-degree angle, opposite over adjacent would be h over 2.5. Solving for h, we multiply by 2.5 on both sides, so the height is determined as the product of 2.5 and tangent 25 degrees. Multiplying, we find that height to be 1.2 miles. Now, I would suppose that that distance is rather deceiving, and the next time you see a shuttle launch, if you see it on video or maybe you're lucky enough to see it in person, just realize that all of the elements involved in it are extremely large, and therefore the distances can be quite deceiving. It appears that things are much closer because of the size of the vehicle involved.